And so without further ado, we're ready for our first presentation, right? So we are ready for our first one with Federico. Federico's joining us here and he's going to take over. He's going to talk about whether we can have nice things. And so just to tell you a little about Federico and about his career, Federico Mena Quintero is one of the founders of the Genome Project, which is a graphic environment that is used in free operating systems. Before Genome, he was in charge of the GIMP project, which is also an open source project. And during the first days of Genome, he was in charge of part of the original coding documentation for the graphical environment libraries and also applications. He worked in Red Hat Advanced Development Labs in the first desktop versions, and after working in Evolution, Federico specialized in the desktop core at the JTK libraries and the native file manager. Today, he is working at SUSE in the open source distributions and SUSE Linux Enterprise Desktop, and he also keeps the SVG libraries and other libraries. So Federico Mena, I think that's all we have. And for the open source world, congratulations and thank you for being here and for sharing with us. Here we go. The floor is yours.
Okay, I'm going to change my screen here. Yes, can you see my slides? Yeah, we can see them. Perfect, so we will begin. As Julie introduced me, my name is Federico Mena. My pronouns are he, him, and I am one of the dinosaurs of free software. I started working with Linux from 1995, 96. And in 97, we started with the Genome Project at the National University of Mexico. And you know, that is a very popular environment in Linux. And we have a lot of very old software, and I'm going to talk about it later and how we can improve all this, the infrastructure using Rust. This picture that you see here is a part of Mexico City. It's also a very old city with a lot of history. And here we see two buildings. On the left is the San Bernardo Church from the 17th century. And on the right, we have a department store. It's called El Palacio de Hierro. And it's a building that it's from the beginnings of the 20th century. I think it's Art Deco or something like that. And both buildings are old infrastructure that the city is still using. And both buildings already have electricity, both have Wi-Fi. And when all these technological changes happened, they were not demolished, they were just being adapted so that they were being able to have the fundamentals that you need to live. So they now have electricity and Wi-Fi and running water, sewage, all of those things. And in software happens something very similar, although it's really hard to change old software because of all the inertia that it has. But those facades of the buildings, those nice buildings that we see of the church and the department store is what we see and what we use when we interact with the buildings. But very few times we enter into the basement or in the operating room or in the room where all the electricals are wired. Very few times we really see the infrastructure behind it. So I work in that part of infrastructure of all the desktop system. By desktop systems, I mean what you run in your personal computer or in your laptop So for those of us who use Linux, I work in the part that just paints the windows in the screens, the buttons, the engine that paints the text, and everything that you see displayed on screen, all that infrastructure, well, you can't see it. The only thing we can see is the pixels that are painted or the audio in your speakers, but all of this is indispensable. Somebody has to develop it. And this talk is my little way of saying, just realize that we're here and please be welcome. You're welcome to help us. So this part of infrastructure is being called system programming. And this is a way that's sort of very fancy way of saying that it's the infrastructure of the system that you're running or interacting. So what is system programming? So that is very near the kernel, the core of the operating system. The kernel is in charge of sharing the hardware with the software, and the system programming is all the user land, all the initialization system when you start your computer, when you activate your network, when you make the request of HCP to have your computer with an IP address, all the services like SSH, bus, all the utilities of the command line, lscat, find, all of these commands, all the fundamental libraries, the cryptographic libraries, the graphic toolkits to paint buttons. This is what I do. And all the libraries to read files, to decode JSON, decode XML, all the codecs to be able to read files, JPEGs, PNGs, video files, all the tools that you need to operate code, low-level code, all the compilers. All of that is system programming. But all of that is already written, isn't it? So why should we worry about that? Why should developers worry about that? Well, everything has changed a lot in the past 20 years, and that's what I'm going to talk to you about. And it can be improved a lot because programming practices have changed a lot in the past 20 years. So we are going to have an overview of the past 40, 50 years of software. And here is, we really are interested in when Unix starts, you know, these hairy men that you see up there. Those are Ken Thompson and Dennis Ritchie. Ken Thompson is one of the authors of Unix, and Ritchie is the creator of the C language. And they are legends that they already did what they had to do. So Unix, it started in PDP-7 machines. You see here a PDP-11 machine, and those are very big machines. They are the size of a fridge, but they are very slow machines with very little capacity, just a few kilobytes of memory. So that was less than 1 megahertz of speed. There was not microprocessors. You just had fundamental circuits that were huge, and you could hand weld them. There was no internet. And there was no need to worry about security. At that moment, if you fed garbage to a program or a file with an incorrect format and the program crashed, well, they said, well, garbage in means garbage out. So just don't get garbage into your program. Then in the 80s, the microcomputer, the home computers are now popular. Before that, computers were very large, very expensive, and only companies had them, only universities had them. And in the 80s, personal computers start having their moments. So here is Bill Gates bragging about his software. He was selling to personal computers. There was no internet at home. The only people who had access to computers with internet were universities, companies such as Bell Labs, Bell Telephones, and even in home computer environments, or some companies, you could assume that computers were not connected to the network. So they better be reliable, the people there. There was no electronic espionage because there was no network. There was no way to transfer data easily. The only way to transfer data between computers, well, with the floppy disks that had very little capacity, so you can get much information from them. And then in the 80s and 90s, this is how Unix looked like. This is the environment from X Windows with the protocol X11. And everything looked terrible, didn't it? Everything was software made by programmers to programmers, so we had no sense of graphic designs. And the technical limitations were very important. If you were lucky, your machine could deploy 16 colors at the same time. There was very low resolution. Everything was very old. In the 90s, personal computers start being more powerful. Windows 95 looks gorgeous. There is a lot of usability behind. You start having home internet using low-speed modems, telephonic modems. And viruses start happening, but they were like toy viruses. The first viruses that reached my computer was using a game in a floppy. So the only thing it did was just adding a little bit of data to executable files, and it was very funny because your floppy just started to fill out. But the viruses were not harmful. And at that time, we still had the philosophy of garbage in, garbage out. If you just fed a corrupt file to a program and it crashed, you just said, well, it crashed, I will just restart it. But in the 90s starts Linux in 91, and GNOME starts in 96, and it's published in 97. This is a screenshot of one of the first versions of GNOME. You can see that graphic design was our passion. So we had very low resolution monitors. I don't know if this is 800 by 600 or something like that. But you start seeing very friendly environments. This is a screenshot from a little bit later. We have more resolution available, so we can make more interesting screens. Here on the left, we are running the file manager, the Nautilus file manager. And on the right, that's something called Red Carpet. It does not exist anymore. And the spreadsheet, I think it's numeric, and it's very little used now. It's one of the spreadsheets that were available for GNOME. But now we are in 2020. Everybody has a supercomputer in their pocket. Most personal machines are mono-user. It's very rare that you share a computer with other people, and nobody really bothers because people who use their computer at homes use Windows, very little people use Macs, and computers are very highly compatible with data centers. So now they have virtual machines, containers, so a lot of resources are shared. A lot of people has internet. Internet is everywhere, and it's a very hostile environment. Everybody needs a firewall. Everybody needs their software to be designed so that you are not being attacked via the internet, because attacks are now automated. So it is indispensable that systems are highly usable and that everything is secure and that your privacy is considered as fundamental. So what is different from the 70s? So in the 70s, the kernel and everything from the system was written in the C language. You had one CPU, less than 1 megahertz of speed, less than 1 megabyte of RAM. Everyone in your office were reliable. Computers were ugly and hard to use, and garbage in, garbage out. And in 2022, kernel and system utilities are still written in C. And that's the only thing that has not changed. because your phone, well, my phone has 6 cores because it's old, but now modern phones have 8 cores and 8 gigas of memory, and that's a lot more than the supercomputers in the 80s. The GPU of my old laptop is faster than a Reality Engine from 1998 of the machines that were sold in thousands and thousands of dollars by then. So your computer has basically infinite storage capacity. It's very hard to find a hard drive that's less than 1 terabyte. All the internet is hostile. Everybody wants computers and phones that are usable. And if you have garbage in, well, you better have secure software because it's either a malware or a government exploit if you are a journalist or dedicated to human rights. But the kernel and the system are still written in C. So why hasn't that changed? So what are the nice things I wanted to talk to you about? Well, many people has used Python, Ruby, Node, JavaScript, and those are very nice languages with very nice tools. All these tools are assuming that internet is available, and they are very friendly languages. They don't let you do anything bad to the memory. They know, for example, that Git exists or that internet is available. And comparing it with something very old like the traditional grep, well, you use grep when you're editing your code and you just edit in Git and it's kind of uncomfortable. And these utilities are being replaced by RG that's written in Rust. So if you're looking for something between source code tree, there's probably a .git there, and you shouldn't get there because it will not deploy anything useful. So grep is still useful for all utilities. So what happens is that the world changes, and what seemingly does not change is because it has a lot of inertia. And as Sarah May says, we sometimes think that awful code is written by awful devs, but in reality, it's written by people who had very limited or very different circumstances of what we have now. And I'm going to tell you a horror story of when we were writing this in the year 2000, we were writing Evolution. It was a Microsoft Outlook clone. We wanted to write an integrated software to read email, to have calendar, to have an address book, a contact list, just like Outlook. And individual utilities to write that started in 1998, right after we started with Genome, but were rewritten after the year 2000 to build Evolution. So this function that's here written in C is one of my first patches in Evolution is completely incorrect because I'm here creating a stack buffer, and now I return a pointer to that buffer in the stack, so that is automatically a corruption of memory. And that bug is fixed 2 commits later. But we had a language that didn't stop you from doing those mistakes. All the time you had to be aware so that these things didn't happen to you. We didn't have an automated compilation system, computers were slow, and nobody thought of recompiling everything all the time to see if it actually worked. So every programmer was responsible to install the development utilities, all the libraries and dependencies in their computer to be able to compile the software. And we wasted a lot of time with that. There were not automated systems to install dependencies or anything like that. So did we really live like that? Yeah. Genome started in 1997. And the version control system then was CVS. It's something terrible that nobody uses except OpenBSD. And GCC just a couple years ago changed from that to Git. So that's the conversion for the genome compiler. So that was an odyssey. So in genome, we changed to use SVN at around the year 2000, and we started using Git much later. The system for bug monitoring that we used in GNOME, I think we set that up in 98. That was something called Bugzilla. It's a very old system for bug monitoring. And when Netscape released the source code of Mozilla, then from Netscape and Mozilla in 98, they also released the bug monitoring system called Bugzilla and automated compilation system called Tinderbox, written by Tara Hernandez and Mozilla, invented basically the continuous compilation concept. Because the problem that they had in Netscape is that they had to support Windows, the 16-bit version, the 32-bit version, old Mac OS, before it was written as Mac OS X, and 8 versions of Unix, 8 different Unix systems. At that time, there were Solaris, HPOX, Linux, all of those. So they said, well, we have to maintain the code of Netscape compiling in all those platforms, so let's write something automated. So that was Tinderbox. We tried to install Tinderbox in Genome, in Symbian, in Evolution, and no, we couldn't make it work in any way that was acceptable. It required a lot of computers compiling all the time, and we did not have the money to install servers that were just compiling all day long. We did not have a framework for automated testing. Old Evolution code has no tests. Old Genome code does not have tests because there was no frameworks to write them, not like Rust that we have the hashtag text. And now we have unit tests, and now that was just until 2007. So we had 10 years without a standard way to write tests. And at the beginning of the 21st century, it sounds very primitive. Git appeared in 2005. Genome started using it in 2008. We had to convince all the people from using Subversion to Git because people from Ubuntu and Canonical wanted to use something else. GitHub was released in 2008. Then then something free appeared for GitHub, but it already disappeared. GitLab is from 2014, and Genome started using its own GitLab instance in 2018, and that changed everything because now we could have bug monitoring, Git repositories, automated compilation, everything was integrated. And we are talking about 2018, that was 4 years ago. So we went from, well, if we started in 97, it's 21 years. We had 21 years without an automated compilation system integrated with our source code. Linux containers started in 2015. They were invented in Joseph Russell, working in Docker. So we spent a year without having containers that didn't need to be routed into the system. And it was very hard at that time. Unix always had something called change root to create a tree, a directory tree, besides the normal tree. and it was very hard to install change root because you need all the spaces to have that, and hard drives were very slow. And how to create all the files, the file root, all the directories for all those files. So it was very obscure utilities and very hard to use. So to create reproducible environments for development was very hard. And the typical status of a project was that they didn't have automated testing because there was no framework. They didn't have continuous integration. There was no reproducible environments because there were no containers. So I started being in charge of Libre SVG for the vector files SVG and renders it into pixels. So there was nothing of what I've been talking about, no automated testing, no nothing. And we have been fixing it little by little. We have Git. The user interface of Git is terrible, but it is a very reliable way of managing code, but there are ways to make it nicer. You can use it from VS Code, from Emacs, from Vim. So you just don't need to battle the Git command line. We already have frameworks to make automated testings in any language, and it makes easier to review the patches made by people. We have continuous compilation. We already have the hardware to compile the software all the time. And we already have mechanisms to make pull requests and merge requests. And we have development logs. It's easier to send patches. We already have virtual machines, containers everywhere. We can create reproducible environments. And for the first time, we have a language, a low-level language that can be integrated with C++ and that it has all these nice things: automated testing, memory save. And this has resulted in the spirit called Rewrite It in Rust. Check this blog. I will send you my presentation later so that you can check the links. All the core utilities are being rewritten in Rust. Those are the basic genome utilities in the command line: cat, cp, chmod, chown, sort through. All of this is being rewritten in Rust. And it's not absolutely necessary to rewrite in Rust because it's already there. But if we want to move little by little out of the mindset that everything is written in C and in insecure languages, maybe it's important. There is a very nice utility that analyzes all the history of development of a Git repository and creates graphs such as this. Every color in the graph is the code that's being added in certain year and if it's being rewritten. So something that happens in a typical project is that code is added and little by little it stays there. But this happened with Libre SVG, the project that we imported from C to Rust in the entirety. So in 2016, we started writing it in Rust. And you can see that the color bands on the left are almost disappearing when they go to the right. And new bands, new code are being started after 2016. That's the code that we rewrote in Rust. And this graph shows that 0% is on the lower part, 100% is on the upper part, and the percentage of lines of code per author. So people who contribute to Libre SVG years ago, before 2016, do no longer contribute. So as we rewrote all the code, their contributions have been reduced to 0. And the contributions from the new people that arrived to write Rust are here shown at the right. So here we have a history and see who has been writing code. So what have we learned in the past 20 years? Well, it's not acceptable to say, well, it works in my computer. You need to have a reproducible environment where to recompile and run your test. So you need to have code coverage to see what parts are not being tested. You have automated compilation. And what about continuous integration? It has been very hard to integrate this in a lot of parts of genome because we didn't have it until a few years ago. So we have Flatpak for applications that live in containers. They are distributed in little packets that can be installed without affecting the rest of the system. And all the compilation and continuous integration is being done through Flatpaks. So do we still have time, a little bit of time, so that I can explain how to integrate Rust into C? Well, we're going to check that very quickly. This is an introduction to introduce Rust into C. This is a very small C program. You can see the definition of a struct that has 3 fields, A, B, and C. It has a Boolean, an integer of 64 bits, and another Boolean. If we ask C to print the size of this structure, it prints 24. And why does do that? Well, we have an integer of 64 bits and 2 booleans of 1 byte, so it should be 10 bytes, but the structure is 24, and that is because each field in C must be aligned according to the data type. Integers have to be aligned to 64 bits, to 8 bytes. So after the first Boolean, after A, there are 7 bytes, seven blank bytes. Then comes the field from 8 bytes, B. And then after that is the field C. And then after C, there are another 7 bytes. So that the size of the structure is a multiple of 8, which is the size of its biggest field. And well, if we print the addresses in memory of each of these fields, we can look at it like this. The field A, it's at the address C0, it's a multiple of 8. Next field is B, another multiple of 8, and the next is C, it's another multiple of 8. So that's a huge structure. If we write an equivalent version in Rust and we ask for the size of the structure, it gives us a smaller structure. And that is because Rust has the ability to reorder the fields in the structures to minimize its size. So what Rust is doing here, the numbers above are regarding the structure according to the Rust memory array, and below are the structure defined in C. This is why we have the symbol and C. So here's what we have. And what Rust does with its own structure is that it minimizes the size of the fields because it rearranges them. So if we want to integrate it with C written code, we have to tell Rust to get the structure and make a memory array in a way that it's equal to the structure in C. And we do that with repro C. We have a small program in C with the same structure as before, and we add a function and it prints each of the fields. So here we initialize a variable with a structure and we call the function that prints. So if we want to port this function to print from C to Rust, we have to declare an identical structure in Rust with repro C and import this function. Let's see how we do that. We have to get this structure, define the function, and let the C code to call it in the same way. So let's see how that's done. We copy the structure definition, we fix the syntax so that it's Rust instead of C, and we write the symbol and repro C so that it is the same memory array. And we define the function, and the symbol no mangle means that do not change the name of the function in the compiler. Pop extern C, that means that the call conventions of this call are the same in C, and we tell that the function should be called, well, it gives us a pointer to a structure called hola, and we make a conversion to a Rust reference using unsafe, and below we call println. And that's the same thing that our function did, so we print the fields. And then going back to our code in C, we remove the function definition and we enter an extern declaration. So we tell the compiler that that function is no longer defined there, but it's being defined outside. So then we have to tell it to the linker to link the code in C to the code in Rust. But if you see, the main function below has not changed. It's printing in the same way that it did before. And in our cargo.toml is the same way as a normal Rust module, but instead we are going to create a static glyph in the create type. That is something like you see below in Unix. It's a file.a. In Mac OS, it's going to create a .lib, and in Windows, it's going to create, I can't remember the libraries in Windows, but anyway, it creates a static library that we can link with our C code. So we link the code and it works. And the strategy here is the one that we follow at LibreSVG. It's exactly that, porting each function from C to Rust and relink every step to see that the code still works. And since you port a couple of functions, you can refactor and make your Rust code better, prettier. Because if you see that the code we have here, it's a little bit ugly. Usually in Rust, we don't want just raw pointers, we want references. So if we refactor this code so that it takes a reference instead of a pointer, and we refactor this duplicated code so that it calls another function, we can do that little by little. LibreSVG was a library of 30,000 lines of code. I'm going to return here a little bit. And before we Rustified this, we had 30,000 lines in C without problems. But when we started to port to Rust, the lines of code started to rise until they were almost doubled. And the reason why they were almost doubled is because the extra code is testing almost all the functions have a unit test in Rust, so the amount of code grows, but it's much more reliable. You can have the trust that if you make any change, you can see if it's broken or not. We just do not need more code in Rust or in C to do the same thing. It's just that here we have the luxury of having tests. So we port the code, we arrive to the beautiful world, and here is how we will port little by little code from C to Rust, and I think our time is up. So thank you very much for attending my talk. I hope that I inspired you a little bit to keep maintaining the old infrastructure and modernize it. We still have to put everything in it: testing, automatic compilation, port it to secure languages. It can be Rust, it can be Haskell, it can be C, it can be whatever you want, but we need to replace little by little the infrastructure because it's insecure and old with nicer things. So that is all. Wow, thank you so much, Federico. You made us remember a lot of things throughout all the history of code. And unfortunately, we are a little bit over time. So if you have any question for Federico, please remember that you can be at the chat of the event, and he can also be found as at Federico Mena at Twitter. So you can set your questions there. Thank you so much for the time and for your great talk. So we will continue with Ramon and Pilar in the next stream. Thank you. Goodbye.